Okay, so this next unit is about energy. Energy, you've probably heard of it. Um, and we talk about, oh yeah, I don't feel like I have much energy today, or that. We throw around the word energy in a lot of different contexts, like pretty casually. What exactly does it mean in physics? Well, there's different ways that we could define what energy is. I think we have a pretty good intuitive sense of what energy is. We could define here energy is the capacity, or the ability, if you want, you could say that too, the capacity to change things. That's a pretty loose definition, but I think it gets at the idea of what energy is. And you might have also heard somewhere in some other science class, or maybe just out in the world, this little physics soundbite that energy can't be created or destroyed. Energy is never created or destroyed. It's just moving around. And we're going to use that idea. It's going to be an important idea to us to sort of do our accounting of like where energy is and what kind of energy, what form it's taking. Okay, so there's some basic ideas about energy. We need to talk about the forms that energy will take, and you know a little bit about this too, I think. You know that there is something that is called kinetic energy. The word kinetic means motion or moving. And that is the energy that something has. Simply by virtue of the fact that it is moving. If you think about something like baseball, for example, if a baseball is just like, sitting right here, let me get a ball to demonstrate. Not that you couldn't imagine what that looks like. It's actually a softball. Ironically named object softball. It's not very soft. So here's a softball, and it's just sitting there. It does not have any kinetic energy. But if we gave this to a softball player, softball pitcher, let's say, and she gave it a good pitch, put a good move on it, then it has, while it's flying through the air, moving at whatever, 60 miles an hour or something, it's got a lot of kinetic energy because it's moving, because it is moving. So this is not a hard thing to understand. Things that are moving have this kind of kinetic energy. And we might think, we'll get later in the unit, we'll get into like making an equation for it, but you might think that the kinetic energy associated with something will have to do with how fast it's going, and maybe also like how big it is, like how much mass it has. All right, we are going to symbolize this with energy. I'm going to put this out at the front. Sorry if that messes up your notes here. E sub k. So energy with a little k to indicate that it is kinetic. And the next one, we know that you've probably heard of this one. This is the potential energy that things have because they are higher up than they might otherwise be. So like if I lift this ball up here, like off the little platform here, It has some gravitational potential energy. It's like potentially it could start acquiring kinetic energy, because and this energy is like stored up, not in my hand. It's really stored up like in this relationship between the earth and the ball. That if I let go, boom, it's going to start falling. So it's gravitational potential energy. So that's the energy something has because it is not at its lowest point that it could be, like relative to the earth, like sitting on this table or the ground or whatever that lowest point would be in that situation. There's also energy, what we're going to call EE. That is energy stored in some kind of like elastic or a spring, something like that. So for example, we have a spring here. This one is attached to this cart right now. If I have this spring here and I compress that spring, there is energy stored in that spring. And if I let go, then it wants to push off that way and make some change in the world. In this case, accelerating that cart. So we're going to call this elastic potential energy. If you're wondering, well, what are the equations for all these things? We'll get to that, not in these notes. Elastic potential energy, that's an energy stored in a spring, or elastic, stretchy cord. It could be a rubber band, whatever. Anything that can stretch out that wants to like go back to where it was. And those are the main three that we're going to be interested in. The other thing we're going to kick around a lot is what we're going to call E-dis. Not for disrespect, but for dissipated energy. Energy can't be created or destroyed, but we observe all the time, like if you slide something across a table, it stops. So where did its energy go? Where did that like kinetic energy that it had, where did it go? It was dissipated by, in that case, by friction. And the form that that energy takes, it doesn't disappear. It's in the form of heat, sound, light sometimes, depending on the situation. All of these are ways in which energy can be dissipated or sort of like leak out of your system. So it doesn't disappear, it just kind of leaks out. So we're just going to call it dissipated energy. Whatever form it's being dissipated in, we're going to lump that all together as dissipated energy. Energy lost from whatever our system is. System just means like the collection of objects that we are thinking about. All right. And there's some other things that we might talk about a little bit at the beginning of this unit, just to consider them, like chemical energy, the energy stored chemically. Like, for example, when you go to the gas station and you fill up your car or your truck with gas, there's energy stored in there, obviously. That's going to be like the energy that your car uses to get from here to there, or from there to here, depending on where you start. So that's chemical energy. It's like stored in the chemical bonds of the gasoline, which is highly combustible. That's not something that we're going to mess with much. but I'm going to put it here just because I think there's at least one example in maybe the 1B assignment that where you need to think about chemical energy. So that's the thing. It's not really, that's more for, I guess, obviously for chemistry than it is for physics, but whatever. So I could probably think of some other things there. We'll leave it here. Like there's like nuclear energy, which is like the energy that's like the bonding of the nuclei of atoms is very, very powerful. If you can break that apart, then an enormous amount of energy is released. But again, that's not really for us in physics, or at least this kind of physics. So, what to do with that information? What we are going to do is learn how to do a little bit of accounting here with energy pie charts. And the idea for the first little bit of this unit is just to get an idea qualitatively, in other words, no numbers, or like what's happening in different situations with energy. So I'm going to give you a couple examples, show you what I'm expecting you to do with these energy pie charts. So how about if you had an object, a ball, and you're going to drop that ball. And we're dropping it, so its initial velocity is 0. And then like at part way down, it's going to be moving pretty fast. And then just when it gets to the ground, it's going to be moving fastest. That's not hair on the ball there. It's that's little marks to show you how fast it's going. And then at the end, it's going to just be sitting. I'm going to redraw. It will just be sitting there with a velocity of 0 again, right? So what's going on with energy? Well, here at the start, if I make a little pie chart here, all of the energy that this ball has, it has, not because it's moving. If its velocity is 0, it doesn't have any kinetic energy, but it's been separated from the ground or the floor, whatever this is here, by some height above that. So it has gravitational potential energy there. So the whole pie, all of the energy that it has, would be gravitational potential energy. And then when it's about halfway down, I'm going to make a new pie chart here that goes with this point in the story. It's moving. It's not moving like the fastest it's ever going to be moving, but it's definitely moving, so it has some kinetic energy, and it's also not at the lowest point that it's going to get to. So this pie is like a split between kinetic energy and gravitational potential energy. And then when it gets to the ground, not when it hits the ground, but just when it gets there, it does not have any height anymore, so it doesn't have that gravitational potential energy because it's separated from the Earth. It's just got all kinetic energy. And then it hits the ground and maybe it rolls around a little bit and stops. And now it's at the 0 height and it doesn't have any speed, so it doesn't have any of either one of these. Where did the energy go? Well, it made a noise, and maybe there was a little bit of friction or whatever. I don't know. The shape of the ball changed, and that takes some energy, but we're just going to lump that all together as dissipated energy. And that just gives us a little way to see, like, as this happens, what's going on with those, with the energy, right? How did I know, in this case, in this example, that there was no EE, there was no elastic energy? Well, there's no spring or elastic, so there's no elastic energy. Pretty easy to tell. Let's see, what else? Let's do one with a spring. So let's say we have a situation where I've got a spring and like a little block compressed up against the spring, and I'm going to release the block and see how far it goes. So let me just show you what I'm talking about here. This is actually a brick. That's a little heavier than what I had in mind, so let's see if I can get that to work. So I'm going to push the brick or block or whatever it is up against the spring and then let go. Now this is pretty heavy. This is like more than a kilogram, so it didn't go very far. Let me see if I can find the wood block real quick. Show you that. Where's my wood blocks at? I got one around here somewhere. Hold on. Hold on. There we go. All right, so here's a little wood block with the sad face on it. And I compress it against the spring and then let go, and it slides across here and it stops. Okay, so let's do some little energy pie charts for that. So here, this is the speed of it right now is 0, the spring is compressed, and then I'm going to do here when it's going, and then here when it is stopped again. And I'm actually going to make two charts that are kind of right at really, really similar times to each other. This is like right before this is released, and this second one is going to be right after it's released. And then here, and then here. Do 4 pies altogether. Okay, so here it has not been released yet. Now I want you to notice that this block does not change height. So that means I do not have to deal with, just like this one, there was no spring. If you have a situation where there's no change in height, you don't have to mess with gravitational potential energy. So what's going on here? Well, at the very beginning, all of the energy is stored in the spring. It's not moving yet, so it's all EE. And then like right after when I release it, all of the spring energy turns into the kinetic energy of the block. And then here, it's still moving, but not as fast. Where's the other half? What's going on? Well, it's kind of grinding to a halt there. There's friction here, and that causes heat and makes the energy dissipate. And eventually it just stops here, and all of the energy is dissipated. So there's another example for you. And I think that probably that is enough for you to go ahead and try to make some pie charts for that first assignment. You might want to try with the first assignment going back and forth, like you try one and then watch what I do and then kind of bounce back and forth with the video for it. All right, to be continued.